Okay, it's it's rainy today, but we have got a pretty good setup, I think. So here, check this out. That's not bad. Unfortunately, though, there is a weird bug with this camera lens, where since it's so pointed over, the camera's angled like this, right above the page, that the zoom does not have a lock on it. So if I try to um, zoom in a little bit more, the thing just starts sliding down until it's all the way zoomed in, which is too far. So I don't know what to do about that. But let's just get into this. Just start studying, man. I was trying to get it set up with my desktop, but there's just no way to get it really how I like it. I mean, there is. What I really want to do is build like some sort of cantilevered arm so that I could get it directly over my page, or maybe not directly over because then my head blocks it or something like that. But you know, there's a solution there that I just don't know. Oh, that's interesting. Okay, but they don't really explain why. Parallel pipette. The determinant of the matrix determines how much the area changes when it is multiplied by a matrix. Yeah. We can discover the definition for the 3x3 determinant watching what happens when an invertible 3x3 matrix is row reduced. Wait, I'm trying to figure out what the row operation there is. What is that? Jeez. Wait, what the? Oh, okay. That's kind of cool. Hey, what's up, Wolfenstein? Bro, today, whenever I'm working inside, dude, I swear it's like a totally different thing. It's like, I don't know. It's rainy today, so I can't film outside. Okay. Okay. For any square matrix of Aij, denote the submatrix formed by deleting the ith row and the jth column. So A3, 2, so then you get this 3 by 3. Okay. We can now give a recursive definition of determinant. Wow. It seems like determinant is then, it must be like a dynamic programming thing, right? If you're doing that recursive thing, there's probably a lot of duplicated work. We'll figure that out. Okay, for n greater than or equal to 2, the determinant of an n by n matrix is the sum of the n terms plus minus with the plus and minus signs alternating. Wait, can we see that? Oh, you alternate them. Okay. The plus and minus signs alternating where the entries are the first row of A. Man, what a crazy formula. So it's the sum alternating plus and minus of the jth element of the first row times the determinant of A1J. So, okay, so let me just say if I have like A, B, C, D, E, F, G, and I take A1, 1, and you remove the, okay, and you just get dude, I swear it's so annoying. You buy pens. Why am I using this pen? You buy 12 pens and like 2 of them are good. I love G2s, but their quality control is terrible. Okay, I understand this operation now. This IJ thing. But yeah, it's recursive because you have to like if let's say you have a 4 by 4, then you're gonna have 3 All right, let's just try to use this formula to compute a determinant. All right, I'll do that. Okay, so this is A, and we want to compute det of A. This is going to be equal to the sum from 1 to 3 of minus 1 to the 1 plus, let's say this is j is equal to 1 plus j, and then this is times a1j det a1j. Man, I wish I could zoom in just a tiny bit more. There we go. Okay, so the first one, j equals 1, then minus 1 to the 2 is 1. All right, so that's a positive, so then we're going to get times a1j times a det a11. So a11 is this, EFIJ. So then det a11 is equal to EH minus IF, I think. Wait, is that the whole formula? I don't know if that's... I think that's the whole formula. I wonder if I can do this. Where's my... Okay, so that's enough. So yeah, so A is equal to this, and I'm pretty sure I can do this. Nice. Okay, so what I did is I this is the formula for removing one. So now we can call that, yeah, EI minus FH. Okay, so we did that. So now the lighting is not very good. That's kind of part of the problem here. Let's see if I can improve that. Maybe that helped a little bit. I don't know. Maybe it did, maybe it didn't. So this is gonna be, so this first entry is gonna be A EH minus IF. Okay, then j equal 2. We're gonna get minus 1 times B times det A12, which is equal to minus B det A12 is going to be DH minus GF. And then finally, j equal to 3. You get... Yeah, the shadows actually suck. Yeah. Because it changes the white balance, right? It's all right. It's all right. It's fine. So then we get 1C. So C times det of this is DI. Okay, so this whole thing is the answer. And we can double check if that's true with computing det A should give us a symbolic thing. A times E minus B times this plus C times. Okay, cool. So that's the correct determinant. All right, we can go back now. Okay, an example. Okay, notation. To state the next theorem, it is convenient to write the definition of det A in a slightly different form. Given a matrix A, the ij cofactor of A is the number Cij given by this formula is called a cofactor expansion across the first row. Okay, that's fine. It's just a different way to write the formula. I don't really care about that. We omit the proof. The determinant of an n by n can be computed by a cofactor expansion across any row or down any column. Dude, determinants are crazy, man. What the hell? Okay. Oh, okay. So this is a good example because then you're like, well, I am never going to take a freaking 5 by 5. But then they show you really only have to take. Yeah, right. If it's in like this kind of row echelon form. So the cofactor expansion on the first column, all terms equal to 0 except the first. So we have 3 times the det of this inner thing because you remove this and that. Okay. So then you're going to get 3 times det of this. So you get 3 times 2 of det of this. And then you have to do a... Oh, and this is the same as before. Oh, okay. Cool. Oh, wow. If A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal. How big can a determinant be? Let A be an n by n matrix. Notice that taking the determinant of A consists of adding and subtracting terms with n. Wait, I don't understand that at all. What? Notice that taking the determinant of A consists of adding the subtracting. I don't really know what that means. Wait, what? Oh, okay. If a computer from. All right, should we do this? So what we should do is we should pick this is the row to cofactor expand, right? So, um, so I'll write this one out. Hello. Wrong one. Okay, here we go. So we're gonna do take det of how many are there? It's a 4 by 4, so this is 5 0 5 0 minus 7 3 minus 8 5 2 0 0 0 2 minus 4 3 6. Okay, so I think we can rewrite this, right? Like, so we're gonna. Okay, so what we're gonna do? Let me just write out the formula. So it's gonna be like, um, it's gonna be like 2 times the det of A 1 3. Then it's gonna be like plus 0 times det A 2 3, and then plus 0 times, or let's do it here, plus 0 times det A 3 3 plus 0 times det of A 4 3. So these all go to 0, so then we just have to take 2 of det A 1 3 is equal to. Oh wait, and actually I messed this up because it would really be like minus this plus this minus this. But that's fine because the zeros make it equivalent. Hello. Okay, so now let me think about this. So now the det of A, so first off, let's just write A13. So A13 is going to be equal to this matrix with this removed. So it's going to be 0, 3, minus 4, 5, minus 8, 3, 0, 5, 6. Okay. So I'm pretty sure what we want to do now is we need to take the determinant of this. And if we pick this to cofactor expand, we're going to get 0 minus 5 times det A 2 1. So, or we could call this B maybe. I don't know. We could call this, because this symbol would refer to a 3 by 3. Anyways, it's fine. So in here, A21 is a 2 by 2, and it's going to be 3 minus 4 5 6. And so the det of this is 18, or here, let's do this. 3 times 6 minus 4 times 5. So this is 18 plus 20, 38. So then so we're going to get, so we have this. So it's going to be 2 times minus 5 times 38. And then this is plus 0 here because we have a 0 here. So 2 minus 5 times 38. We can check if this is right. I'm not convinced that I'm right here. 2 times minus 5 times 38. Oh yeah, what am I talking about? This is a 10. Minus 380. Okay. Let's do this. Okay. Okay, so I definitely did something wrong. All right, we got to figure out where I went wrong. I think this first part should be right. That you take the Wait, but you know what I think is wrong? Hello. I think what's wrong is the plus minus thing. I think like you need I think you need to because plus minus plus. No, I think that's right. So it's gonna be 2 times the debt of this. Let me make sure that I wrote it down right. That's always something that I do wrong. 5 minus 7, 2, 2. 0, 3, 0, 4. Minus 4. Minus 5. Bro, come on. Minus 5, minus 8, 0, 3. 0, 5. Minus 6. Dude, how do I always do this? So this is minus 5. This is minus 6. So we're going to get minus 5 times the debt. So, yeah, 3, 5, minus 4, minus 6. So we should get minus 18 plus 20, which is 2. You replace this with 2, and you get minus 10 times. Hold on. This is minus 18 plus 20. This should be minus 20, but I think that I still have it wrong. I think that it's positive 20. Let's see, where did I flip the sign? Oh, because actually this becomes minus minus because in this cofactor expansion you get a 0 minus 5. Okay, is equal to 20. All right, we did it. We figured it out. Took a little bit, but that's what it is. So it's 20. All right, we can switch back over to here. Start looking. Okay, so let's just make sure that we did it right. Go down. See, how did they do it? We begin right down the third column. That makes sense. Maybe value by expansion down 2. Oh, yeah. So I need to remember that. That's important. That you do this minus 1 I plus j. So you get, and minus 1 to the 4 is 1. So you get times 2. Then you get -1. This is the second column, first row, so it's a 2, so that's a minus. So this is 2 times -1 times -5 times the det of this. All right, we got it. Easy peasy. All right, hopefully we can just bang this out, and maybe we can do 3.1 and 3.2 in one sitting, because our class is actually rushing through this. It's going through it really fast. All right, so we're gonna read through the problems, select maybe 10, do them, and then continue. I'll be right back. Okay. Get on with it. All right, compute the determinants using a cofactor expansion across the first row. Also compute the cofactor down the second column. Compute the determinants by cofactors. At each step, choose a row or column that involves the least amount of computation. Oh man, it's a lot of just computation. Whoa, what the? The expansion of a 3x3 determinant can be remembered by the following device. Write a second copy of the first two columns to the right of the matrix. Compute the determinant by multiplying entries on 6. That's silly, man. See, that's the thing is there's so many. These are all just tricks. I don't like that trick. We're not going to do those. If it's not general, it's like, what's the point, you know? You have not done 4 row and column yet. We'll do some of these. I'll walk through these because these are nice because on all of these cases you really only have to do see how there's zeros along this whole thing, and there's only one element that's non-zero on here. This one's triangular, so technically we can just multiply the like, okay, let me think about this one. 12 is a good one. All right, so let's write down which ones we want to do. So I'll do a couple of the first section. My rule is I pretty much always do one from every section unless the section's really, really silly. So let's just do we'll do one. We'll do 3. Okay, we'll do 9. I don't know if I want to do 9. We'll do 12. So we'll do 1, 3, 12. Should we do a 5 by 5? I feel like that's going to be really annoying. Okay, we're going to skip these 4 because I don't want to use that trick. I really don't think I'll ever use that. All right. 19 to 20, explore the effect of an elementary row operation on the determinant. In each case, state the row operation and how it affects the determinant. Okay, this one is actually pretty cool. We're going to do 19 for sure. Let's do 20. So 20 is scalar multiplication. This one is interchanging rows. What is this row operation? Maybe we'll do that one. Okay, I don't want to do the 3 by 3s. All right, compute the determinants of the elementary matrices. That seems pretty fun. So what you're going to get here, you can see immediately. So we take this cofactor expansion so that we have 1 times the determinant of this 2 by 2, and which is going to be 1 minus nothing. So, wait, really? I think that's true, but if you multiply this by ABC, you're going to get A times this first column, B times this second column. So this one, the determinant is 1, because you're going to get 1 times 1 minus k times 0. All right, I like these ones. These ones are pretty good. Let's do 25. This one should also be 0, right? Like if we take this, we're going to get, yeah, so we'll do 27 because 27 is fast. Oh, I wanted to do 26. Okay. All right, so we'll do those 3. This one, see, okay, if it's diagonal, I'm pretty sure it's just the product of, if it's a diagonal matrix, it's the product along the main diagonal. And it's not even, you don't even need it to be a diagonal matrix. I think you only need it to be a triangular matrix. Okay, along here, I think you can just let me think about this. 28 actually is good. I like these problems where you just sort of get an intuitive feel for what the operation is. But 29 and 30, we'll just like talk about them. So this is clearly going to be, let's say we expand along the first row and first column. Then we're going to get 1 times the determinant of this 2 by 2 in the inside. The 2 by 2 determinant is going to be k times 1 minus 0. So this whole thing is just going to be equal to k. And it's the same for here. You're going to get k times 1. So we don't need to do those two because we just did them. Give reasons. What is the reason? What is the determinant of an elementary row replacement matrix? 31 seems good because it's an explained thing. What is the determinant of an elementary scaling matrix with k on the diagonal? Because we need to look in these definitions. I forget what these mean, so I'm going to do that one too. Ooh, this is good. Verify that the determinant of the matrix product, well, but is E is an elementary matrix. So is it the case that, yeah, so this is actually, is this in general true? That's kind of what I want to know. Is it true that the determinant of E times A is equal to the determinant of E times the determinant of A? I don't think that's in general true. But we'll definitely do 33. And then do 37. In exercises 39 through 42, okay, I always do true falses because they're pretty fast and they really test your understanding. So we're gonna do 39 through 42. What does that mean? Compute the area of the parallelogram determined by you. $43 is good because I mean honestly that's what's kind of crazy about this whole section is the best intro to is I mean I like the geometric understanding of the determinant. It's just stretching and it's basically a ratio of the area or a description of how the area expands. All right, so 43. Do 43. I usually write down a lot of problems and then I don't do them all, but it is nice to read through them. Oh, I know what it's saying. Okay, so yeah, okay. These are the 4 points of the parallelogram. Okay, I understand what this problem is asking now. So you draw 4 dots related to those 4 vectors, and then you compute its area. We'll do that. I don't know if we need to do 44 though. Maybe we'll do 44. Maybe we'll do 44 on the computer. Wait, all of whose entries are numbers that are greater than or equal to minus 10 and less than or... Wow. Oh, we'll do 45. 45 should be quick. If we think about... All right, let's say we have 10 and 10 on the main diagonal, and then on the other two, let's say we had a minus 10 and a 10. Then we should get 100 minus 10 times 10, which is equal to 200, I think. So I'm pretty sure that, like, okay, so if we were to do this, let's say A is 10, 10, minus 10, 10, and we did det A, we get 200. So I think that that's the maximum that you could possibly get. I don't know how you could go further than that. So 45 basically, and the minimum would just be minus 200, I think. So maybe we'll like double check that on the computer, but I think that we just answered that one. Let A be a 3 by 3. All of these entries are... Oh, another one of these. Oh, the trick for a 3 by 3, huh? Maybe we need to read that. Maybe we need to read this reasonable answers thing in more detail again. All right, but I don't really want to do that one. Okay, I always like these T ones because these T ones are kind of fun. Construct a random matrix with integer entries. How is the inverse of the determinant really? Ooh. 47 is a great problem. Whenever you actually have to think about what the operation's doing, what is the inverse? So the inverse... 48. We're definitely going to do 48. Is it true that the debt of the matrix product AB is equal to the debt of A times the debt of B? Yeah, that sounds fun. Ooh, 49. Would definitely do that. Construct a random 4x4 matrix A with integer entries between -9 and 9. Compare debt with debt of A transpose, debt of -A, debt of 2A, debt of 10A. No, wait, let's do this. Wait, whoa. But if you take this, so it's okay, wait, hold on. Okay, so this is minus 0.02. But 10A is minus 2. So it's not times 10, it's times 100. Like if we were to do this, we get 100. That's kind of interesting. And then here, you get a 10,000. So I think it might be, if you have K times debt A, is it equal, or, no, if you have debt A, KA, is that going to be equal to K squared times debt A? I think that might be true. Because look, let's do 4 times debt A. But why is that true? That's so random. Okay, if we have just like A is equal to A, B, C, D, and then we do K times, or K times A, then we have this thing, and we take the debt of this, we're going to get yeah, but does that continue for 3x3s? I don't know if that continues for by 3x3s. Let's do, let's say, so now it's okay, so it's actually, so for A that's n by n, then debt of KA, yeah, is equal to K to the n times. That's pretty interesting. I don't know if that's true, but it seems true. Problem 43. Hold on. Let's go. How do you draw the picture? All right, let's do that one right now. Okay. So 43. All right, we're going to go back to the other ones, but let's just do this one right now. So 43, U is equal to 3, 0. V is equal to 1, 2. We want to compute the area, right? Compute area of the parallelogram formed by U, V, U plus V, and 0. All right, so let me just do this. Okay, so we have 1, 2, 3. So this is U. U. Can you see that? It's a little small, but Okay, and then 1, 2, this is v. Okay, then u plus v is going to be 3, 0, plus 1, 2 is equal to 4, 2. So 4, 2 is going to be here, and then 0. So what we're going to have is a parallelogram like this. Okay, so the base is 3. Wait, is that true? Oh, and this is also 3. And this is 2. Because this is 1 and this is, so this coordinate is 1, 2, 4, 2, 3, 0, and 0, 0. So that's how you draw the parallelogram. So then the area is equal to, I think it's just 3 times 2 is equal to 6. Okay, that's problem 43. All right, let's go back to finishing reading the problems, though. So yeah, 50 was really good. 50 I started looking at. I started looking at make conjectures about how these determinants are related. Yeah, so we only did this, and we found that the scalar multiplication of determinant, it gets taken to the power of the size of the matrix, really. Recall from the introductory section that the larger the determinant of D transpose D, where D is the design matrix, the better will be the accuracy of the calculated weights for small or small light objects. Which of the following matrix corresponds to the best design? See, I still don't know why that is. That's so cool. We'll do this one just to, well, maybe we'll do that one. I don't know. Okay, so I think we have all the problems that we need to do. Let me just write them all down in my computer. 1, 3, 12, 19, 20, 21, 25 through 28, 31 through 33, 37, 39 through 45, 47 through 50. All right, so we have a whole bunch of problems to do. Let's just get started. All right, problem 1. All right, so this problem is compute det A using cofactor expansion on first row. It says also along second column. Okay, so for 1, A is equal to 3, 0, 4, 2, 3, 2, 0, 5, minus 1. Okay, so along the first row, we're going to get, so we're going to get minus 1 to the 1 plus 1, because this is A11, times A11, which is 3, times det, and then this is that special notation, A11, where A11 is equal to removing the first row in the first column. So this is going to be 3, 2, 5, minus 1. And the det of that is going to be equal to minus 3 minus 10. Okay, so we're going to get 3 times minus 13. Then we're going to get minus 0 times det A 1, 2. And then finally plus 4 times det A 1, 3. Which is, we remove the first row in the last column. So this is going to be 2, 3, 0, 5, which is equal to 10. The det of that is 10. So we're going to get minus 39 plus 40 is equal to 1. Okay, I'm going to double check that. Okay, so does that make sense that we had a 0 here so we could save a little bit of time? So we only really had to take 2 by 2 determinants. Pretty good. All right. And I am correct. Okay, so we got the right answer for number 1. Now we have to do it along the second column, right? So now we're gonna get so 0. So we're starting along this column. This is gonna be 1, 2. So we're gonna get minus 1 to the 3 times 0 times det A 1, 2. But this becomes 0, so we don't have to compute that. Then we're gonna get plus minus 1 to the 2, 2. So 2 plus 2, that's just 1 times 3 det A 2, 2, which is, and then let's just write out the rest. So plus minus 1 to the 2 plus 3 times 5 det A 3, 2. All right, so this is 0, so we can just get rid of that. This one is going to be, let's say A22 is 3, 4, 0, minus 1. And A32 is equal to 3, 4, 2, 2. Okay, so then this determinant is going to be minus 3 and is equal to det A2, 2. This one is going to be 6 minus 8 is equal to minus 2. All right. So our final expression is going to be 1 times 3 times minus 3 plus minus 1 times 5 times minus 2. So this is going to be minus 9 plus 10 equal to 1. Let's double check that, but I think that that is what we have. So, oh wait, of course it's 1. We just did it in a different way. Okay, so that was actually kind of good. So we showed that no matter that, we didn't prove it, but we at least showed that, we took it across a row and we took it across a column and we got the same answer. All right, so that's problem 1. All right, I am going to skip problem 3. So let's just write a few of the 12, 19, 20, 21. All right, so problem 12. Okay, we're going to take the determinant. Take the determinant using least amount of time. Time or energy. Wait, did I want to do 9? Here, we'll do this one. We'll just do this one. 3, 0, 0, 0. 7 minus 2, 0, 0. 2, 6, 3, 0. 3 minus 8, 4 minus 3. All right, so we need to take the det of this. So, oh, sorry. There we go. Okay. So So we're going to go across this one, and then we're going to go across this one. So we're going to get minus 1 squared, because of 1 plus 1, times 3 times det A11. So now we're going to get the det of, so let's just write this, A11 is equal to minus 2. So I could just recognize that this is a triangular matrix because there's zeros all of there. But we're just going to do this one way, and then we're going to just check that it equals the product along the diagonal. So minus 2, 2, 6, 3, 0, minus 8, 4, 3, minus 3. All right. And then it's going to be zeros along the rest of this. So this is going to be plus 0, or, yeah, minus 0, plus 0, minus 0. So now we just have to take det of A11. So the det is going to be, we're going to do it along this first one again. So this is going to be minus 2, or wait, let's do this. Minus 1 squared times minus 2 times det A11. And I don't like that we keep using A, because this A11 and this, these are two different A11s. This A11 refers to this one. But in any case. All right. So we're going to get, I'll call it A11 prime or something, but it's going to be 3, 0, 4, minus 3. And this is going to be minus 9, minus 0. Okay, so what are we going to get at the end? Oh, and then this is going to be, plus minus 0 plus 0. So in the end, we're going to get 3 times minus 2 times minus 9 is equal to 54. 6 is going to be 6 times 9. Let's see. So we're going to get, on the trace, we're going to get 3. Trace means the product of the diagonal. 3 times minus 2 times 3 times minus 3 is equal to 54. All right, cool. That one was easy. But the trick is recognize that it's a triangular matrix. Okay, so we did problem 12. Let's do problem 19 now. Okay, explore the effect of an elementary row operation on the determinant of a matrix. All right, so let's say, so 19 we have A, B, C, D is our original matrix. And so then the det of that, we'll do that. And then finally we have C, D, A, B. All right, so this is going to be AD minus BC, and this is going to be CB minus AD. So, so the effect so if we were to multiply this by minus 1 times minus 1, so let's call this A and let's call this B. Then det A is equal to minus det B. So that's the first one. I wanted to do 20. Let's do 20. 20, we have A is equal to A, B, C, D. B is equal to A, B, K times C, and K times D. All right, so we're going to get AD minus BC again, and then we're going to get let's do AKD minus BKC. So we can factor KAD minus BC. So the det of A is equal to K times the det of B. It'd be interesting to see how that changes in bigger matrices. All right, 21. Do we want to do 21? Let's see, what else do we have? We have so many problems to do. I think we could skip 21. Okay, then 25 through 28. Let's just do 25. Okay, problem 25. Compute the determinant of the following. So we have 1, 1, 1, okay, and all the rest are zeros. So because this is triangular here, let's fill in the zeros. Then we know that the det is equal to 1. So we could see that in another way. It's going to be 1 times det of 1, 0, k, 1, which is equal to 1 times 1 minus k times 0 is equal to 1. So then we're going to get 1 times 1. The determinant is 1. Let's do number 26. Okay, this one's interesting. So it's like they flipped the identity matrix. So we should get so if we do our cofactor expansion along the first row, we should get 0 minus 1 det a1 2. a1 2 is equal to 1 0 0 1, which is just the identity, which is det equal to 1. So then we're going to get minus 1. Now, if you see what this does to ABC, let's do ABC. We're going to get B times 0 1 0. Oh, wait. This just permutes the first two. All right. What's next? Okay, so wait, we're planning to do, we just did 25, I think. Yeah, we just did 25 and 26. So we were planning to do 27 and 28. But the thing is, this is triangular. So really, this is just going to be 1. Now, this one's interesting, but I think that this is going to be minus 1. Because let's do the expansion. Wait, is it? This is going to be 1 to the 1 plus 3, which is, so this is even. So that's a plus 1 minus 1. All right, let's just do this. So if we take A is equal to 0, 0, 1, 0, 1, 0, 1, 0. So this is like the, is it actually, hold on, I'm going to say if we do I3, if we permute this, Oh yeah, because you flip it along. Oh, yeah. Okay. So I don't know what that operation is called, but if we take det A, it's gonna be -1. Yep, that's what I thought. So we don't need to do 27, 28 because you can just notice it. And then this one's gonna be k, and this one's also gonna be k. So we're good there. Let's see what other problems do we want to do. 31 through 33. Oh, these were good. These were good. I remember that. What is the determinant of an elementary row replacement matrix? Because I don't even know what that means. So let's just do some. I think it's where you like. Okay. The determinant of that is 1. And actually, is it the case that I think it has to be the case. What's the use of matrix in real life? Everywhere, bro. A row swap flips the sign of the determinant, and row scaling. Okay. All right. So the determinant of a row replacement. So for 31, row replacement preserves determinant. For 32, though, so okay. So what is elementary scaling matrix? I think that that's. I think that that's just where you've scaled a row. Yeah, is one where you multiply a single row by a non-zero scalar. Okay, so yeah, so for 32, uh, the det of E, which is the elementary matrix, is equal to K, yeah, times det of I, or yeah, it's just K. All right, cool. Um, and okay, so we did those. Now we wanted to do problems 37, 39 through 45. And that's good for now. Okay, so 37. We didn't want to do. Oh, we didn't. Oh, let's do 33. All right. Problem 33. Verify det EA is equal to det E times det A, where A is equal to A, B, C, D, and E is equal to, for problem 33, it's 1, K, 0, 1. So this is one of those row replacement LM complementary row replacement matrix. So therefore, det, can you see everything sometimes? Okay, good. Det equals 1. So this det is going to be AD minus BC times, okay, so let's compute E times A is equal to 1K 0 1 A B C D is equal to, so we're going to get A plus KC, B plus KD, C D. And man, I wish I could zoom in just a little bit more. Okay. So in the determinant of EA is equal to D times A plus KC minus C times B plus KD is equal to DA plus DKC minus CB minus CKD. So this cancels and this cancels is equal to, all right, so we verified it. This is AD minus BC. So it preserved it. So we're good there. All right, what's the next problem? 37. Okay, so it says A is equal to 6, 5, 3, 4. And 2A is equal to 12, 10, 6, 8. Is det 2A equal to 2 det A? So the determinant, so det A is equal to 24 minus 15, because we have 6 times 4 minus 3 times 5 is equal to 9. Okay, det 2A is equal to 16 plus 80 is 96 minus 60 equal to 36. Is that true? Let me just double check that that's right. 12 times 8, 96 minus 60. Okay, cool. So that's correct. So no det A, 2 det A is not equal to det 2A. What it is equal to, though, is 2 squared times det A. That's what we figured out like 10 minutes ago, is we just started experimenting and we found out that that was the case. All right, problem. So this was 37. All right, now it's time to do 39. I think these are true false. So we can just walk through these true false. All right. An n by n determinant is defined by determinants of I believe that's true. Yes. So that's true. All right, number 40. The ij cofactor of a matrix A is the matrix Aij obtained by deleting its ith row and jth column. Yep, that's true. 41. The cofactor expansion of det A down a column is equal to the cofactor expansion along a row. Yep, that's true. It would be a totally worthless definition if that wasn't the case. The determinant of a triangular matrix is the sum of the entries on the main diagonal. That is false. It's the product. All right, so it's time to test these. So I got true, 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 false. True, det A is defined recursively. False. Oh, wow. Okay, yeah. So I was being a little careless. Okay, 2 is false. That's actually true. Okay, 2 is false. Because in the definition, they define, let's see, where's the cofactor? The cofactor is given by the, you need the minus. Okay. All right, what's up? True and then false. Cool. All right, what's next? We want to do 43. No, we already did 43. We did 43 at the beginning when Anjana asked it. Okay. 44, we don't need to do 44. The only thing that we didn't do here, actually, in 43, is we did not compute the determinant of the columns. So if we did 3 times 2 is 6 minus 0. So, in fact, the area of the parallelogram is equal to the determinant. And so this is probably one of the best problems in the section so far. So we're not going to do this one. Oh, maybe we could do VU. If we permuted this, it was 1, 2, and then 3, 0. It would be minus 6. So if you switch the columns, it becomes minus 6. Okay, that's pretty cool. All right, I think we already talked about 45. Basically, if you have, because didn't we do this 10, 10? Yeah, if we did this, so this is, anyways, you can go back and look at that one, but we already did that one. We're not going to do the 3x3 one. We are going to do these, though. These are good. Let's see, how long have we been doing? An hour and 30. That's kind of on my target. I don't think we need to do too much longer than that. So what's left? Let's see here. We have just 47 through 50. Okay, I'll be back in a minute and we will do those problems. You can read them if you want. Okay, I'm back. Let's do this thing. Construct a random 4x4 matrix with integer entries between 9 and 9. Minus 9 and 9. How is det A inverse related to det A? That's sick. Okay, so let's do that. So A is equal to rand minus 9 to 9, 4x4. Okay, det A, det inv A. All right, so basically, oh wow, that's actually so sick. So det A inv A is equal to inv det A. That's really cool. Okay, so yeah, so det A inv or det inv A is equal to inv det A. That's really cool. All right, 48. Is it true that det AB is equal to det A times det B? Oh, it is. Wait. Oh, actually, that's interesting. This should be the same, right? Oh, wait, is it? Yeah, wait. Is it? Yeah, it is. So, okay. So it's always really small. So it does seem like in general this is true. Cool. 49, is it true that det A plus B is equal to... No, I doubt that's true. Wait, let's try to think if we can come up with it without using a computer. Okay. What if we did this? So let's say A is equal to I of 2. Then B is equal to 0, 1, 1, 0. Det of A plus B is 0. But det... Oh, wait, actually? Okay, wait, actually? All right, let's do our... Oh, wait, we can copy this. Oh, that's not always true. What the heck? How is it true that one time? It's like definitely not true. But what's a good example? Product with some it doesn't hold. No, what? Oh yeah, I should have taken two identities. Yeah, this is clearly because you're gonna get 4 versus 2. Okay, let's see what else do we got here. Um, so okay, so this one we already know. If you do minus, you can pull out the minus actually. Wait, can you? Um, because here, depending on the size, this is gonna be 2 to the 4. This is gonna be 16 times this, and this is gonna be 10,000. But what about det A transpose? Wait, hold on. Okay, so yeah. Okay, so det A transpose is equal to det A. That's fine. That's cool. But now det minus A. I think it probably is. If you think about the cofactor expand, oh really? Oh yeah, that's what. Okay, yeah, that's right. That's crazy, man. That's so what a weird pattern. That is really goofy. Right. This is the yeah, because it's a scaling. That's super weird. All right, are we done here? All right, I think we're done. All right, that wraps up the section 3.1